You ever wonder how the side view mirror on a car gives you that huge, wide view? Or why a straw in a glass of water looks like it's broken? Well, I promise you, it's not magic. It's just really cool physics. In this explainer, we are going to pull back the curtain on the elegant math behind mirrors and the super weird way that light can bend.
I mean, it seems kind of complicated, right? You move an object, its reflection moves too. But is that all random, or is there a predictable pattern? Well, believe it or not, there is. And with one single, surprisingly simple formula, we can pinpoint its exact location, down to the centimeter.
And the reason we can do that is because there is a fundamental mathematical code, you could say, that governs how all spherical mirrors work. Once you get this code, you can predict what any reflection is going to do.
And here it is. This beautiful little equation is our master key. It connects u, the distance of the object from the mirror, v, the distance of the image from the mirror, and f, which is the mirror's focal length. With this thing, we can solve for any one of these if we just know the other two.
Okay, but before we can just jump in and start plugging in numbers, we need a set of rules. Think of it like a map legend, right? We have to agree on which directions are positive and which are negative. This system is called the New Cartesian Sign Convention, and it's absolutely crucial. The main idea is that we measure everything from the pole, which is basically the center of the mirror surface. And honestly, the rules are super straightforward. Any distance you measure to the left of the mirror, that's negative. Any distance to the right, that's positive. For height, anything above the main central axis is positive, and anything below it is negative. That's it. Just remember those 4 simple rules. All right, so now we know where the image is going to show up. But that's only half the story, isn't it? What's it going to look like? Is it going to be bigger, smaller, maybe even upside down? This brings us to the next big piece of the puzzle, magnification.
So magnification, which we just call m, tells us exactly that. It's just the ratio of the image height to the object height. But here's where it gets really, really powerful. Magnification is also equal to the negative of the image distance divided by the object distance. This connects the size of the image directly to its position. So elegant.
But you know what's maybe the most powerful thing here? It's simply the sign of the magnification. Seriously, that little plus or minus tells you a whole story. If m is negative, it means the image is real and inverted. It's literally upside down. If m is positive, it means the image is virtual and erect, so it's upright and looks like it's behind the mirror.
Okay, we've got the formula, we've got the rules for the signs, we know all about magnification. Let's put this all together and crack a real problem taken straight from our source material.
So here's our scenario, based on a classic textbook problem. We've got a convex mirror, like a car's side view mirror. It has a radius of curvature of 3 meters. And there's an object, let's picture another car, that's 5 meters away from it. Our job, find exactly where that reflection is going to appear and what it's going to look like.
First things first, and you cannot skip this step, we apply our sign convention. Now, because it's a convex mirror, its focus is behind it, so the radius r and the focal length f are both positive. The object is in front of the mirror, so to the left, which means its distance u is negative. Getting these signs right is everything. All right, now for the fun part. We just take these values, with their signs, and plug them straight into our mirror formula. We know f and we know u, so we just need to do a little bit of algebra to solve for v. And boom, there's our answer. The image distance, v, is positive 1.15 meters. So what's that plus sign telling us? Remember our rules? It means the image is formed 1.15 meters times behind the mirror.
And for the final piece of the puzzle, we calculate the magnification using our v and u. The result is positive 0.23. So let's decode that. The positive sign confirms the image is virtual and upright. And that number, 0.23, tells us it's much smaller than the actual object, which is exactly what you want from a side view mirror.
So that's reflection. That's how light bounces. But light doesn't just bounce off things, does it? It also travels through them. And when it does, well, something very strange happens.
And that's where we enter the amazing world of refraction. This is the science that explains why things look bent or kind of displaced when you see them through water or glass.
Check out this incredibly simple but kind of mind-bending experiment. You put a coin in a bowl, just so you can't quite see it over the rim. Then, without moving your head at all, you have a friend pour water into the bowl. And like magic, the coin just reappears. How does that happen? The light coming from the coin is actually bending as it leaves the water.
This whole phenomenon is called refraction, and the core idea is pretty simple.
Whenever light passes from one medium, like water, into another one, like air, it changes direction. It literally takes a turn.
Now, to really see this bending in a super controlled way, physicists use a classic setup that involves just a simple rectangular block of glass.
So let's follow a single ray of light on its journey. It starts in the air, goes to this block of glass, and then comes out the other side. And right away, you can see its path is not a straight line at all. Let's break that journey down. First, as the light enters the denser glass, it actually slows down a bit and bends towards an imaginary perpendicular line we call the normal. Then second, as it leaves the glass and goes back into the less dense air, it speeds up again and bends away from the normal. And third, and this is so cool, notice how the final ray leaving the glass is perfectly parallel to the first ray that went in.
And that right there is the big takeaway from the glass slab experiment. The light doesn't permanently change its direction of travel, it just gets knocked sideways a little. We call this a lateral displacement.
Which leads us to one last really fascinating question. We just said that light slows down when it enters glass and speeds back up when it leaves. But wait a minute, haven't we all been told that the speed of light is, the one great constant in the universe? This little experiment seems to suggest something else. So, can the speed of light actually change? Now that is something to think about.